Okay, so let's begin. So this statement is attributed to Gauss that number theory is queen of mathematics. And this statement is so profound that it is considered among famous quotes about mathematics. So what in fact selecting these problems is that we highlight what is the sense that number theory is queen of mathematics. What is the sense in the statement? We will make some attempt to justify that. Of course, there are so many things, but here there will be some attempts. So history is full of anecdotes where we are told that even if you make lots of arrangements and a lot of resources are used, still it's difficult to please a queen or to make a queen happy. And at times, yes, people do some very minimal thing and queen is happy. So that is the kind of characteristic of queen I have chosen. There are several other things attributed to queen, but in history we have these characteristics as well, and that's what I have taken here. This fits to my narrative. So there are many problems in number theory which are not resolved in spite of huge efforts and in spite of using developments from all branches of mathematics. So a lot of efforts, lots of resources, still the problems are unresolved. On the other hand, there are problems which are resolved with some good amount of efforts. There are problems which are resolved. So this is more or less, you see that the bullet number 3 and bullet number 4 is saying that, well, if you have kingdom of mathematics, then in bullet number 2, what these anecdotes you have heard about, you can replace number theory by queen. So that is the sense I have in mind. I see that somewhere. I think I have to do a full screen somewhere. Maybe that's not possible. Okay, so yeah, I see that the titles are not visible. So fine. I think this headings of slides is not readable, right?
No, they're not readable.
Yeah,
One can't see them.
Right. Sorry, yeah, it's not visible, right? So yeah, this is a Riemann hypothesis. So actually, I think I won't try for that now because in iPad I don't know if I can make a full screen and things like that. So this is a description about Riemann hypothesis. Well, this is not the problem I want to talk about, by the way, but just to fit that previous narrative on the previous slide, that what is Riemann hypothesis? It's a famous problem in number theory, and almost each branch of mathematics has an equivalent statement. So what it says that in each branch of mathematics you can work, whatever branch you work in mathematics, you can work in your choice of mathematics and yet you may be resolving Riemann hypothesis. Riemann hypothesis, I write RH. So that means what I'm saying that each branch, more or less, whatever major branch of mathematics you pick, you do have an equivalent statement for Riemann hypothesis. So you solve that branch and then that will take care of Riemann hypothesis. And most of the mathematicians, most of the top level mathematicians have definitely made an attempt to solve Riemann hypothesis. In fact, little more, that some physicists are also trying to solve Riemann hypothesis. And how they are trying to solve Riemann hypothesis, in fact, that's a very famous talk. I think it can be found online by Professor Sunil Mukhi, where he describes something called Riemann gas. So where properties of some properties of this gas are related to the zeros of this function. So Therefore, now this Riemann hypothesis is a problem for, I mean, even physicists consider it as a problem in their domain. Okay. But yet it is far from being solved. We have more or less, in fact, no reasonable progress. So, but as I said, this is not the problem I want to discuss about. It just fits the narrative that there is lots and lots of efforts from several branches of maths, in fact, from outside maths as well. Yet we are far from making any reasonable progress. So for that, I wanted to mention this. Now I go to the problems which I definitely want to discuss in this talk. And the first problem is Fermat's last theorem. So there are three problems I want to discuss for today's talk. First, Fermat's last theorem. What is Fermat's last theorem? Fermat's last theorem says that for any n greater than 2, there are no non-zero integers x, y, z satisfying x raised to n plus y raised to n equals to z raised to n. So now I think most, in fact, I believe everybody, each one of you must be aware about Pythagorean triplets. That there are several integer solutions to the equation x square plus y square equal to z square. If you take n equal to 2, then there are infinitely many solutions to this. In fact, one can characterize the solutions and you can write down that for any integer u and v co-prime, you can take x equal to u square minus v square, y equals to 2uv, and z equals to u square plus v square. Then you will see that x, y, z with, for any choices of u, v, they satisfy the equation x square plus y square equal to z square, which is same as this equation for n equal to 2. So for n equal to 2, there are infinitely many solutions. In fact, you have a parametric solution that can take x equal to u square minus v square and so on. But what Fermat asserted that for n equal to 3, for any n, in fact, for any n greater than 2, there are no solution. So where for n equal to 2, you had infinitely many solutions, for any n bigger than 2, you have no solution. That is what Fermat's last theorem asserts. Fermat himself showed that if you take n equal to 4, then there are no solution. That this equation which I have here on the screen, this equation, you call it star because later I start numbering, but here I did not use numbering. So call it star. This equation star has no solution for n equal to 4. This was achieved by Fermat. And more or less just because of this, we can make that, remember that what you are trying to prove, you are trying to prove that this equation star has no solution when n is bigger than 2. So in that I'm saying because of this, you can actually assume that n equal to p is an odd prime. So this is a small reduction. This is small reduction and I will discuss this later. So that means if you solve without loss of generality, assume that n equal to an odd prime p and solve that the equation star with n replaced by p has no solution, then you are done. Fermat's last theorem is proved. That reduction I will discuss at a later stage. So apart from progress made by Fermat himself that n equal to 4, there were also some solutions for small values of p. For example, p equal to 3 was solved, p equal to 5 was solved. P equal to 7 took a lot of time, but that was also solved. So, okay. several branches of mathematics came in existence on the way to the final solution. So to try Fermat's last theorem, it turned out that several branches of mathematics were developed to solve it. Some did not succeed, some eventually succeeded. And my research is mainly focused in this branch of algebraic number theory, A and T, and that was also developed as an effort to solve Fermat's last theorem. Okay, so this was eventually, Fermat's last theorem was eventually resolved by Andrew Wiles in 1994, and it used machinery from number theory, algebra, analysis, geometry. Those are the major branches we can think of, and I'm mentioning those. Otherwise, if you want to mention something else, you can. Okay. So see, the idea of, the method I'm following is the following, that I will first just mention these problems very briefly, and then develop some thread combining these three, like which is common to these three problems. And then I will talk a bit more about these problems and maybe my connection to these problems. So that is the plan of the talk. So now I'm at the stage where I'm mentioning this first part, that okay, what are these three problems? So any comment about Fermat's last theorem till now, if anybody has something? Okay, so no comment, then let us go to the next problem. Next problem is called Catalan conjecture. What is Catalan conjecture? Catalan conjecture says that basically what Catalan did, he was looking at this list of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and he said that these two numbers are special. 8 and 9, they are special. They are special in what regard? They are special in the regard that they are next to each other. After 8, 9 occurs, there is no in between natural number, and then they are perfect power. They both are perfect powers. What are perfect powers? Any number of the form a raised to k, where a belongs to z and k is a natural number bigger than 1. So any such number which can be written as power of some integer, proper power. See, every number you can write as that number power 1. That is not a perfect power. So that power should be a proper power. That means exponent should be bigger than 1. Is called a perfect power. So Catalan said that these two are the only numbers in this list which are perfect powers. After that, for example, if you go, in fact, before that itself, 4 was a perfect power, but numbers adjacent to it is 3 or 5. None of them are perfect power. And if you go to the next perfect power in this list, that will be 16, but number adjacent to 16 are 15 and 17. None of them are perfect power. So this is an assertion about the full list of integers, that these are the only guys which are perfect powers and next to each other. Okay, so let's realize the statement in a different way. In terms of what you call Diophantine equation, this conjecture is that the following equation, x raised to m minus y raised to n equals to 1 among non-zero integers x, y, and numbers m n greater than 1 has only two solutions, namely x equal to 3, m equal to 2, y equal to 2, n equal to 3, and x equal to minus 3, m equal to 2, y equal to 2, n equal to 3. Oh, no, y, sorry. So there is a switch here. It should be here. This should be, well, it's correct, but yeah, it's better to write here y and here m. But though it's correct because they both have same value. So no issue. So please understand here that unlike in Fermat's last theorem, see in Fermat's last theorem when we were discussing that, we kind of fixed an integer. We took that, okay, fix an integer n bigger than 2. And then we are making the statement that, okay, this is not true. And then we prove that statement for each n. Whereas here, we are not doing that. Here we are doing that, we are taking that, okay, you take mn also as variables. So here mn are also variables. So this is an equation in 4 variables, and with 2 of them appearing in exponents. So you call these exponential Diophantine equations. Okay, this is the statement of Catalan conjecture that this equation, which again I have not given any number, let us give it double star. This equation has only 2 solutions, namely 9 minus 8 equal to 1, but 9 can be written as 3 square or it can be written as minus 3 square. So either way. Once again, the smaller cases, like when exponent is small, like a case when m is 2 or n equal to 2, this was resolved separately. And because of this resolution, one could assume that m equal to p and n equal to q are odd primes. So once again, I am saying that there is some reduction involved, and this reduction is what I explained earlier, that the same kind of reduction is involved once again. Okay, so this I will explain once again later, that you can make such an assumption. Good. And this Catalan conjecture eventually became a theorem in 2002 to 2004, when Mihailescu proved it using a lot of machinery from algebraic number theory and some new tricks, some new ideas he developed. He could prove this, and then it became Mihailescu's theorem. So I write 2002, 2004 because until 2004, the solution used a lot of computation using computers. So in 2004, what Mihailescu did, he managed to avoid all the computer added computations. So that's about Catalan conjecture. Any question or comment? I hope the statement is very clear. You are basically looking double star, let's say. All right, so let us move to our next problem, which is the final problem I want to talk about. This is a conjecture due to Bunyakovsky. So Mihailescu's theorem or Catalan conjecture also remained kind of unsolved for around 150 years. This remained unsolved for 150 years. And then next in the list is Bunyakovsky conjecture. What is Bunyakovsky conjecture? Bunyakovsky conjecture is that let fx in zx be a non-constant polynomial. So remember that we are taking polynomials with integer coefficient only. And assume that fx is irreducible, number 1. Number 2, that there is integer k values of this polynomial f. Sometime it may happen that there are k divides all the values of polynomial. I don't want that to happen. If that doesn't happen, then Bunyakovsky said that fx takes infinitely many prime values. Okay, so please understand first, okay, what I said, that there are polynomials whose all values are divisible by a fixed number. Let us illustrate that quickly. Consider this polynomial fx equal to x into x plus 1, right? So you take any number n, f of n is product of two consecutive numbers. And in your BSc, I think you must have studied that maybe third year. Yeah, certainly by third year, that product of any two consecutive numbers is divisible by 2. So any fn is always divisible by 2. So 2 divides fn for all n. Therefore, here see, in this fn, that's why we need such a condition like this. Of course, one can say that is this polynomial irreducible? No, it is not irreducible, but then that we can make a small tweaking to get a irreducible polynomial. For example, you can take 2 plus 2. That will be an irreducible polynomial. I assume that it must be that x square plus x plus 2. Yeah, so neither plus 1 nor minus 1 nor plus 2 or minus 2 are a solution. So yes, this is irreducible polynomial, and still 2 divides fn for each n. So that is why condition number 2. So what is assertion? Assertion is that if these two conditions are satisfied, then this polynomial fx takes infinitely many prime values. There are infinitely many primes which appear as value of this polynomial. That is what the assertion is. In fact, there can be a very good talk about prime values of polynomials. How this is quite explored problem that see, primes are very important, and especially when we look at applications of mathematics, they are even more important. So a lot of people have explored, is there a easy way to generate primes? And there cannot be an easier way other than if you can find a polynomial whose all values are primes. But unfortunately, nothing like that happens. So there is a very good literature on that. And in fact, people have gone to polynomials in several variables. So sometime maybe. So all right, coming back to this, we want our polynomial to take infinitely many prime values under these two conditions. First, I want to assert that these two conditions are necessary. See, these two conditions are necessary. If a polynomial doesn't satisfy any of these two conditions, then it cannot take infinitely many prime values. Not possible at all. Well, let's see why. Condition number 1, if fx fails to be irreducible, means fx is reducible, then you can say that fx equals to f1x into f2x, right? And now you see f of n equal to f of, for any number n, f of n equals to f1n into f2n. This guy is going to be prime only when is prime, only if not, it is not sufficient, it is definitely necessary that it is prime only if f1n equals to 1 or f2n equals to 1. But given a polynomial, how many times it can take value 1? Only finitely many choices, right? So there are only finitely many choices of n such that f1n will be 1. There are only finitely many choices of n such that f2n equal to 1. For all other choices, this is different from 1, this is different from 1. Therefore, you have a factor of fn. You always have a non-trivial factor of fn. So fn cannot be prime, except finitely many choices of n. So that says that condition number 1 is necessary. Condition number 2, I already said that if you have a fixed divisor, what are you saying? You are saying that if condition 2 fails, that means there is an integer k which divides f of n for all n in z. Then this fn can be prime only when fn equals to k possibly. Nothing else will be prime, right? Because k is always a divisor. So condition 2 is also necessary. Okay. These two are necessary conditions, and what Bunyakovsky said that actually they are sufficient as well. Let's go to the next slide. So now I mentioned Dirichlet theorem, I'm sure many of you must have heard. So Bunyakovsky, possibly you, but this Dirichlet, many of you might have heard about it. Dirichlet theorem, if A and B are co-prime positive integers, then the arithmetic progression A n plus B contains infinitely many primes. Okay? That means there are infinitely many choices of n for which this A n plus B is a prime number. Okay. What is its connection to Bunyakovsky conjecture? So, in fact, if you read carefully, then Dirichlet theorem says that Bunyakovsky conjecture is true when degree of fx is 1. So, this is actually a particular case of Bunyakovsky conjecture. This is, let me write just Bunyakovsky conjecture, degree 1 case. Why it is a particular case? Because see, take if fx is a degree 1, fx in zx is of degree 1, that implies fx is of the form ax plus b for some integer a and b, right? And condition number 2 says that you don't have any fixed divisor. So condition number 2, in fact condition number 1 also, but let's remain to the minimal requirements. Condition number 2 says that A and B are co-prime. Right? So A and B must be co-prime, that is condition number 2. So when you have a linear polynomial such that it satisfies condition 1 and condition 2, that means you have Ax plus B where A and B are co-prime, then by this Dirichlet theorem here, it takes infinitely many prime values that says that Bunyakovsky conjecture is true. But all this when degree of fx is 1. So using Dirichlet theorem, you can prove Bunyakovsky conjecture for degree 1 polynomials, and converse also is easy. That see, these are anyway, a n plus b takes infinitely many prime. I will consider the polynomial fx equal to ax plus b where a and b are co-prime. It satisfies condition 1 and 2 by Bunyakovsky. You get that there are infinitely many primes. So Bunyakovsky implies Dirichlet, Dirichlet implies Bunyakovsky for degree 1. All right, so, and there is absolutely no further progress in last, I think, 170 years, or one can say a little more, in fact. So, because this theorem of Dirichlet was actually known before Bunyakovsky made this conjecture. Possibly it was known in 1837, I think. Therefore, it's slightly more than 170 years that we have not made a single progress after that. Good. So these are the 3 problems I wanted to mention. If there is any question or comment, please let me know, either a moderator or somebody, and then accordingly we can see. So no question or comment?
I think so, no questions in the chat box yet.
Okay, great. All right, so let us move. So, of course, we are celebrating Pi week. So I thought, there is a lot of pi already in picture, but I have not mentioned it explicitly. So I thought maybe some explicit mention is a good idea. So let's see one such. What was Bunyakovsky conjecture? Bunyakovsky conjecture was that this polynomial fx should have a lot of prime values, means you should have infinitely many n1, n2, so on, such that f of n1 is a prime number p1, f of n2 is a prime number p2, and you should be able to continue. This should not stop, means there are infinitely many such choices. And see, if a number is prime, means it has no other divisor other than itself, right? So that means it cannot have any square divisor. So if infinitely many values of fx have to be prime, then fx must have infinitely many values which have no square factor. That means there must be infinitely many numbers n in Z such that f of n has no square factor. Well, if it has a square factor, then you take a prime dividing that square factor and you can say that that is p square does not divide fn for any p. And this should happen for any p, and there should be infinitely many such n. So that is about asking how many square free values f takes. Okay. So how many square free values f takes, and there is a conjecture about that as well. In fact, that is also a very, very difficult conjecture. As in case of Bunyakovsky, you have very little progress. Same happens with this square free conjecture. But once again, I am omitting this conjecture for the reason that the thread which binds the three problems I am considering doesn't bind this one. So I will not discuss much about this. However, because of pi, I want to talk about this. Let's see where pi appears. What is the density of square free natural numbers among all natural numbers? So, well, density is a slightly technical term, but I don't want to define that. So what I'm saying, you look at once again all the natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and go on. I mean, I don't know, maybe I will stop at 16. Well, 16, 17, let's stop at 17. That's a good one. So you see this list of all natural numbers. What you are interested in, look at those guys which have no square factor. So this, yes, that's a good number for our consideration. This one. 4 is bad guy. It is a square. In fact, it is a perfect square. So it certainly has a square factor. 5 is a good guy. 6 is a good guy. 7 is a good guy. 8 is not. 9 is not. 10 is good. 11 is good. 12 is not. 13 is good. 14 is good. 15 is good. 16 is not. 17 is good. So you look at these kind of numbers, and question is, what is the proportion of these numbers among the full list? So that's what by density I meant. What is the proportion of these numbers among the full list? And if some of you have seen this answer, that's where the answer surprisingly reflects pi in it. So what is the answer? Answer is 6 by pi square. So now here is the, I mean, I'm not defining this density, etc., but still here is the technical thing. Answer is 6 by pi square means for large real number x, the ratio, you take all those natural numbers less than capital X such that n is square free, and consider the number of such natural numbers divided by cardinality of this set of all natural numbers less than x. So this ratio is almost as it gets very close to 6 by pi square. As you take x tends to infinity, actually it converges to 6 by pi square. That's what I mean by density for the time being, let's say. So you see, you are looking certain proportion and suddenly this pi square comes in. And once again, that as I said, already pi had made its appearance in my previous slides, but not mentioned explicitly. For example, Riemann hypothesis, certainly. I mean, Riemann zeta function, but I was not willing to talk about that. So, but this is an explicit mention of pi in my talk. Okay, so this was a surprising occurrence. Now I want to see what are the combining thread between them. So why did I select these problems? What is the reason for them? So, okay, let's see. Well, I hope you agree that there was a lot of efforts and lots of involvement of various branches of mathematics, and some I mentioned resolved, some are still unresolved. And then what I defined the characteristic of a queen in the historical anecdotes, more or less that supports that, okay, number theory should be considered as queen of mathematics. So that was one reason why I am talking about these problems. Second, I'm talking these problems that they all revolve around a common thread, and that is a certain arithmetic of some rings, which is actually the subject of algebraic number theory. So that is also a reason why I have chosen these three problems. In fact, as I said, that I am not discussing that square free value conjecture. That is the reason that it doesn't, at least, I mean, there is more or less no progress, and whatever progress is, at least I am not aware if it uses anything about Z zeta P. So, okay. So now my introduction to the three problems which I wanted to discuss is over. And what I will do now, I will now introduce some more preliminaries, and now things will get slightly technical. And after preliminaries, I will talk little more about these problems once again. So if there is any question or comment till now, please let me know. If not, then let us move ahead. So we need the arithmetic of this ring, Z zeta P. What is ring?
Sir,
Yeah.
I mean, so just a small question. This we talked about the polynomial. We're having a infinitely many primes, right? Polynomial expressing infinitely many primes. So assuming that polynomial
Yes.
is not a square, can we assure that we'll have infinitely many square-free things? Square-free integers? Polynomial expresses infinitely many square-free integers?
No.
That also we can't
No.
guarantee.
No.
Okay.
No.
Okay. Thank you, sir.
So yeah, that is actually this square free conjecture. That square free conjecture is known when the polynomial is of degree 1 or degree 2 or degree 3. That's all we know. When a polynomial has degree more than 3, then we don't know.
Thanks.
Okay.
Okay, sir.
And also in chat, there was some issue. I think it was about the density.
Yes, sir. There's a question saying, how can we prove the previous problem, the density of square free natural number?
Yeah, that is using CU methods. Okay. Basically, what you know, inclusion exclusion principle, you can use that to prove that statement.
Okay, sir. Thanks.
All right.
Yes, sir.
Okay, so let us move ahead. So we need the arithmetic of the ring. What is a ring? A ring, so I'm sure that the students who are third year or at later stage, they definitely know. Otherwise, what you can say that these are some subsets of complex numbers where you can define addition and you can talk about multiplication. Division is possibly not there. I mean, you are not allowed to perform in this set, but addition and multiplication you can perform. So that's what I mean by ring. So we need this arithmetic of this ring. Okay. So you can look this as a subset of complex numbers. They are almost like Z. In fact, yeah, it's maybe better if I give it here. Yeah, it will be better if I write down this diagram. So you have a field, namely that is quotient field of this set. What I have written there, I don't want to introduce a lot of terminology. So let us take this is a quotient field of this set which is written here. This set contains Q, set of all rational numbers. Inside Q you have integers and there is an analog. Just as Z is inside Q, there is an analog. That is what I am taking Z zeta P. So that's what I mean when I say that this is pretty much like this Z inside Q. Okay. So what more we can do? So you can look this as a subset of complex number. They are like Z. Means when if you add two elements of this set, you get one side. Remember that this is A0, A1, A2. All these are integers. What is zeta P? Zeta P is a complex number such that zeta P power P equals to 1 and zeta P power R is not equal to 1 for any R in 1 to P minus 1. In fact, if you want, you can take zeta P the following number. You can take zeta P to be this number. Once again, our favorite pi appears. Cos 2 pi by P plus I sine 2 pi by P. So you can take this as a choice of zeta P. Cos 2 pi by P plus iota sine 2 pi by P. So therefore, this is a complex number, this is a complex number, this is a complex number. Their product will again be a complex number, complex number, complex number. You can add them once again, you get a complex number. So this is a subset of some complex numbers. Where if I add any two element of this set, result is again an element of this form. If I multiply any two element in this set, result is once again an element of this form. So, but division is not guaranteed. I can, if I say that I divide any element of this set by another element, well, I may go outside this set. What are elements in this set? For example, 2 is a member of this set, 5 is a member of this set. Why 2 is a member? I take A1 to be 0, A2 to be 0, AP minus to be 0, and I take A0 equal to 2. Same logic says that 5 is a member. Zeta P is a member of this set. Why? Because take A0 to be 0, A1 to be 1, A2 to be 0, and so on. Everything else 0. So zeta P is a member. Same way zeta P square is a member. What about zeta P powered, let's say zeta P power P plus 10? That's also a member because this is same as, remember that zeta P power P is 1. So this is same as zeta P power 10. If 10 is smaller than P minus 2, the trick which we use to show zeta P is a member, same can be used. If P minus 2 is lesser than 10, then once again you can go modulo P. So there are several members and there are several complex numbers which are not there. For example, this guy is certainly not there. Pi is certainly not a member of any such set. Whatever P you take, pi is not a member of Z zeta P. So that's first talk about ring. So what is a ring? This set together with the addition operation and multiplication operation is what I mean by a ring. And I will need this quite a lot. All right, so let's go to the next one. So what is an important property of Z which we are interested in? The most important property of Z is the fundamental theorem of arithmetic. That is, any number bigger than 1 can be written as a product of prime number. All must have seen this fundamental theorem of arithmetic, that you take a natural number n bigger than, in fact, the better suited version will be this. 0 1 can be factorized uniquely as a product of primes. See, if you state, so you will see that this is an advantage even here, still this one is. So I can talk about factorization in ZGTP. If I want to take the state here, this statement, then you have to give meaning of what you mean by when a number is bigger than 1. And well, one can do that, but that will involve unnecessary trouble. So it's better to replace that any number, any alpha in this set, such that alpha is different from 0 plus minus 1 and what you call in rings units. So any alpha different from these guys, you can write it as a product of primes in a unique way. Is that true? Answer is no, it is not true. Unfortunately, this property is not true for most of ZGTP. Okay. So what to do then? So this property is not true. What people did, some number theories, they tried to measure that. See, fundamental theorem of arithmetic is extremely important from various perspectives, whether you want to do like a number theory or various parts of algebra, but even for applied application of number theory, it's very, very critical. So people tried to study and they associated something that will measure, okay, fine, that ZGTP is not a unique factorization domain. How far it is from being a unique factorization domain? So there is a number associated to ZGTP which measures this failure, that how far it is from being a UFD, and it is called the class number of ZGTP. We will use the notation H subscript P for denoting this. Okay, HP will denote the class number of ZGTP. So when I say measures, means in fact the only glimpse I can offer here is that this measure means HP. What is the smallest possible number for HP? It's a positive number, so it can be the smallest possible value is 1, right? So smallest possible value is 1, HP is 1, provided ZGTP is a UFD. So that is what I mean that it measures. Okay, ZGTP may not be UFD most often, but the number associated to that will be 1 if and only if ZGTP is a UFD. If ZGTP is not a UFD, then the number will be bigger than 1. And the more this number grows, the more difficult it becomes factorizing something in ZGTP. So by measure, I just mean that HP equals to 1 if and only if ZGTP is a UFD. All right, so let's move ahead. This number HP is actually a cardinality of a group, and that group is called class group. So what is that class group? In fact, once again, I will not define these things, but mainly you can say that you are looking at collection of all ideals inside ZGTP collection of all ideals in ZGTP, and then define an equivalence relation on this collection and look at all the equivalence classes. What is equivalence relation? You say that two ideals I1 and I2 are equivalent if and only if you can write I1 equals to some alpha times I2 for alpha in ZGTP. Well, this is technically not correct, but it's okay for this talk. So if you can do this, where this you take as product of ideals, okay, you can multiply two ideals. So take principal ideal generated by alpha. You say that I1 is related to I2 if and only if I1 equals to alpha I2. So collection of all equivalence classes is what this group HP is, okay, class group HP. So there is a very nice theory which says that if instead of numbers, if you don't look at elements of ZGTP, but look at ideals in ZGTP, then fundamental theorem of arithmetic is true. That means what? That every ideal, every non-trivial ideal in Z zeta P can be factored as product of prime ideals in a unique way, but okay. So, okay, there is no unique factorization, but yes, if you go to ideals, then there is a unique factorization. And these concepts are defined for more rings, which I will take. Z root D. What is Z root D? Once again, Z root D will be collection of all complex numbers of the form A, D, where A and B are. So this concept of class groups and class numbers are defined for them as well. And I use a slightly odd notation. That case, C small ld for class number, C capital LD for class group. All right, so see now. Now next, I think I just mentioned that what is my connection with this problem. My connection with this problem, Fermat's last theorem definitely was solved before I heard about it. In 94, certainly I had not heard about it. And my only connection is, I mean, several people have written over the last 15, 20 years saying that they have. And in fact, one of which somebody sent me that actually got published in a journal, some obscure journal, but it got published. So therefore, I don't have much to do with it other than like, yes, it involves arithmetic of Z zeta P, which I really love. I am much fond of this arithmetic of Z zeta P. Problems are that, so that's the reason why I mentioned this problem. And cat conjecture, yes, in fact, I tried. See the last slide, I had mentioned this one, right? Z root D. If you take D equal to -1, what you get, you call that guy as a Gaussian integer. And this Gaussian integer is what I looked at Catalan's conjecture for Gaussian integers in my research. I also have obtained some annihilators of class group HV. What is annihilator? That I will define in a while. So this class group HP, which was introduced earlier, I have looked at some annihilators. I have developed some new annihilators for that. And I have made some conditional progress. This is very important. I already said that other than Dirichlet theorem, nothing is known about Bunyakovsky conjecture. So I have made some small conditional progress in this regard, that I make some assumption and then say that, okay, some part of Bunyakovsky conjecture, very minor part. So this is my personal connection to this. And now the last segment of talk where I take those problems and talk a little more about each of them. So is there any question, comment, and what about time?
Sir, there's no problem. There's no time restriction. You can go on. That's absolutely fine. And for now, there are no questions in the chat box.
Okay. All right. So, okay, so let's see. I mean, see, if you say 10 minutes, I can wind up in 10 minutes because the last is something well talked about, so I can skip that and go to Catalan, which has significant progress, and I mean it is resolved completely, and I can just take that. So if you say that there is some time limit, 10 minutes or so, anyway, I think we started 10 minutes late, so definitely I guess I have 10 minutes. So this is the reduction problem I talked, right? I said that you can assume those exponent in Fermat's theorem as well as in Catalan conjecture to be prime. So I talk about that. The first bullet let us ignore. In Fermat's theorem. So suppose what I am saying that you prove that there is no solution for Fermat's theorem when n is an odd prime p. You prove that and that is good enough. So you can make that assumption in Fermat's theorem that n equals to p is an odd prime. Why? So suppose there is an n greater than 2 and non-zero integers x, y, z such that x raised to n plus y raised to n equal to z raised to n. That means there is a solution for this n. Now n is bigger than 2. What does that indicate? That says that either n has an odd prime factor, which we call p, or 4 divides n. At least one of these two should be true, right? If n divides p and x, y, z are solution of this equation, then you consider these guys, x raised to n by p. Remember that p divides n, so n divides n by p is an integer, positive natural number. This power p plus y power n by p whole power p equals to z power n by p whole power p. So these are integers. This is thing in bracket is an integer. This is an integer. This is an integer. Therefore, you are saying that you have obtained a solution to Fermat's theorem for some odd prime p. But you said that well, when I assume that n is an odd prime p, I will prove that there is no solution. So this will lead to a contradiction. If you have already proved that there is no solution for odd primes. Same way if, oh, I have written it completely opposite, sorry. Nobody stopped me. So if p divides n, then you have this. If p doesn't divide n, then definitely 4 has to divide n. In that case, if 4 divides n, same thing you can do for 4. X raised to n by 4 whole power 4 plus y raised to n by 4 whole power 4 equals to z power n by 4 whole power 4. And but Fermat already, this is an integer power 4 plus another integer power 4 equals to another integer power 4. But Fermat already said that you cannot obtain such integers. So once again a contradiction. So it is this reasoning that we can always assume in whether Fermat's theorem or Catalan conjecture, those exponents are odd prime numbers. Okay, this I already explained. Now let's go to. So Fermat's theorem, I will be a bit fast because I think I will take some time to explain Catalan conjecture. That's, let's say, more in my control, let's say, whereas Fermat's theorem is not. So I will spend more time on that rather than spending time on Fermat's theorem. So let's go quickly. You are saying that there are no integers x, y, z. Find this when p is an. This is not. Then you can factorize this. Remember that x power p plus y power p equals to this product I equals to 0 to p minus 1. So do this factorization. And then what next? You can actually remember the factorization I have as element level. But, you can do one that go to ideal level. I said at down to ideal level, that will say that these are product of ideals, equal of ideals, but right hand side everything is power. So the amount of say that when these guys are co-prime, each of this x plus zeta p y, x plus zeta p square y, they all are co-prime to each other. Well, not exactly, but okay, more or less, let's say. So you get that this equals to a power p for some ideal a of z zeta p. left hand side is ideal generated by x plus zeta py. If P does not divide HP, then this can be treated, then this equality, which is in terms of ideals, can be actually treated as equality of numbers, in the sense that actually you have kind of factorization in numbers, and then using once again using arithmetic of this ring, you can obtain a contradiction. So there is a great deal in it, but I don't want to get into that. All this was done by Kumar. And Kumar proved Fermat's last theorem when P doesn't divide HP. HP is, remember, that class number of Q zeta, class number of Z zeta P. So Kumar had done that. Much later, it was shown that there are infinitely many primes P for which actually P divides HP. The assumption Kumar needed, P doesn't divide HP, but there are several primes for which P divides HP. So therefore, you needed a new idea, and well, that new idea eventually was too big, and it's even now I consider it's too big for me to mention. So proof used tools from algebra analysis geometry. Solution of FLT means if you have a triplet XYZ which satisfies Fermat's last theorem for an odd prime exponent P, that will give rise to a Frey curve, and a Frey curve are nice elliptic curves. Okay, every Frey curve is a nice elliptic curve. That was proved by Frey himself. And then Ribet proved that Frey curves are not modular. What is modular? Analogy, nothing else we can say about it now. So Ribet proved that Frey curves are not modular, and maybe after 20 years of Ribet, Andrew Wiles proved that all nice elliptic curves over Q are modular. So here you have already said that this is nice elliptic curve. It is a over Q. So Wiles said that they are modular. Ribet said they are not modular. That's a contradiction. So you can see that documentary movie on Fermat's last theorem. It's a very nice movie. Okay, so now we take 10 minutes to go to the Catalan conjecture section, and that will end the talk as well, more or less. So see, we have already mentioned that Z zeta P is not a unique factorization domain for most of P. And that was a problem for Fermat's last theorem, and people developed this class group factorization in terms of ideals, but yet that didn't suffice. Okay. To overcome this problem, people also studied maps from Z zeta P to itself, what you actually call homomorphisms, field homomorphisms, here in this case ring homomorphisms. So people studied all the ring homomorphisms from Z zeta P to itself. Which are 1, 1 and on 2. And this is nothing but a Galois group of Q zeta P over Q, what we are talking about. So take G this group. G is isomorphic to this group, by the way, in this case, but we won't need that. The multiplicative group of residues modulo P. So take this group, and with this group, we consider this group ring. What is ZG? ZG, once again, remember that the way you introduce Z zeta P here, ZG I am introducing, it's slightly different. This is collection of all finite sum n sigma, where sigma is in G. So coefficients are integer, n sigma are integers. And sigmas, remember that G itself is finite group, as I remarked. So this is a finite sum. You'll take all possible such sums and collect all such elements. You can add these guys coefficient wise. You can multiply using the multiplication of G, and this makes this guy in a ring. This is a ring called group ring. And there is an operation of this any element of this, suppose you take an element in this theta, means theta equals to summation and sigma running in G. Then you define theta A. What is theta A? Theta A is product of sigma A and sigma. Where remember that A, what is A? A is an ideal, right? Somewhere I must have said, okay, I have not said. Okay, so A is an ideal. A is an ideal in Z zeta P. So sigma of A is once again an ideal in Z zeta P. Now you want to talk about what is sigma A power n sigma. When n sigma is positive, you can multiply ideals several times. Same ideal again and again, no issue. When n sigma is negative, then remember that at some moment I introduced that you have a group whose members are ideals, right? It was an equivalence class of ideals. So go to that group, and in that group, given any element, you can have its inverse. So if n sigma is negative, take sigma A inverse and then take power absolute value of n sigma. So that is the sense here. And so this is an action of this group ring ZG on the class group of Z zeta P. Or on any ideal or any number of Z zeta P as well. So any number or any ideal. So any element theta in Z zeta G which converts every ideal A of Z zeta P into a principal ideal under this definition is called an annihilator. So at some moment I said I will define annihilator later. Here is the definition. So converts into principal, because remember that class group was kind of that equivalence relation used principal ideals alpha, right? If I can go back, I don't remember which page number. Let's see. Here. This equivalence relation basically was if they are equivalent up to a principal ideal. So something becomes trivial means it becomes principal. So any theta in ZG which says that every ideal A, theta of A is principal, then you say that theta is an annihilator of class group. So, okay, that's definition of annihilators, and then there are several results known on annihilators of class groups, most notably due to Stickelberger and Thine. Suppose, so now we are solving Catalan conjecture, okay? That is the only theorem which I will talk little bit. So we are solving Catalan conjecture. Suppose PQ are odd primes. I already said that you can assume that exponents in Catalan are odd primes. Suppose P and Q are odd primes and XY are non-zero integers satisfying this. You can assume that P is greater than Q. Why P greater than Q can be assumed? That P equal to Q is not possible, first of all. If P equal to Q, you write, see, X, Y are two integer. I can always write X equal to Y plus K for some integer K, right? X and Y are integer, I just take their difference, call that K. So I write X equal to Y plus K. If P equals to Q and X, Y are solution of this, then you have Y plus K power P minus Y power P, because Q equals to P. But now you make a binomial expansion, you can easily prove that this number is always bigger than 1, strictly bigger than 1. So this equality is not possible. So P equal to Q is not possible. Now P equal to Q is not possible means either P is bigger than Q or P is less than Q. But remember that if X is a solution, X power P minus Y power Q equals to 1, then you can also write this as this is a minus Y power Q minus X power P, because P and Q are odd primes. P, Q are odd primes. Therefore, same thing. This equation is written same here. And that says that the role of P and Q can be interchanged. So once you allow that role of P and Q can be interchanged and P is different from Q, then you get P greater than Q. So this was an easy reduction. And Mihailescu used Stickelberger's result on annihilation of class groups to prove the following two identities. One was this one, this congruence, other was P less than 4Q square and Q less than 4 square, both. This is a very nice, laborious proof that from somewhere he gets idea and pursues it. So I certainly won't discuss that, but these two identities, this identities and this inequality he proved, and this was using Stickelberger's result on annihilator. He also used Thane's theory of annihilators to prove that P is congruent to 1 modulo Q or Q is congruent to 1 modulo P. But please keep in mind, we already have started with P bigger than Q. Therefore, we basically have this one. And if you have P is congruent to 1 modulo Q, what can I say? In this case, you can say that P equals to 1 plus KQ because P is congruent to 1 modulo Q. So P equal to 1 plus KQ for some K in Z. Now let us write down this P power Q minus 1 here. Let us try to read this. Oh, sorry. What will be P power Q minus 1? 1 plus KQ whole power Q minus 1. But this is equal to use binomial expansion and write modulo Q square. See, what will be the next term? The term I have written 1 plus K into Q minus 1 into Q. Next term will be 1 plus, Q minus 1 choose 2 into KQ whole square. So K square Q square. Therefore, next term onwards, everything will have a power of Q, higher power of Q. Q square, Q cube and so on. But I am writing modulo Q square, so I am not writing these terms. Therefore, P power Q minus 1 is congruent to 1 plus K into Q minus 1 Q modulo Q square. But what was equation? Equation 3 was that P power Q minus 1 is congruent to 1 modulo Q square. Therefore, this guy should be divisible by Q square. And this is divisible by Q square only if K is divisible by Q. So I replace this K here. This K by TQ for some integer T. So for some integer T, I replace that K by, because Q divides K, so K is TQ. Hence we get P equal to 1 plus TQ square. So P is 1 plus TQ square, but you also have that P is less than 4Q square. Therefore, what are the choices for T? T has to be 0 or 1 or 2 or 3. Only these 4 choices. And each of them easily gives you a contradiction. Let us quickly see that why. What about T equal to 0? T equal to 0 implies P equals to 1. But P is a prime. So contradiction. T equal to 1 gives what? Implies, remember that T equal to 1 means 1 plus Q square. Q is an odd prime. So you have a 1 plus an odd number, that means P is even. Once again a contradiction because P is an odd prime you have taken. What about T equal to 2? T equal to 2, you see that Q is an odd prime, therefore Q square is always congruent to 1 modulo. So Q square is always congruent to 1 modulo 3. Therefore 1 plus 2Q square. 1 plus 2Q square will always be divisible by 3. So you get 3 divides P. 3 divides P and P is prime. That implies P has to be equal to 3. And this contradicts because P is bigger than Q and Q is an odd prime which is also bigger than or equal to 3. So once again a contradiction. T equal to 3 implies P is even. So again contradiction. So these 3 identities or inequalities which Mihailescu obtained using theory of annihilators and his laborious ingenious tools give contradiction to all possible cases, assuming if you have started with a solution to Catalan conjecture. And that proves that there is no solution to Catalan equation other than the case when exponent was 2, one of the exponent was 2. Okay, sorry for this extra time. I am almost done now. Let me go directly to the last slide. That I introduced that this fields, right? At some moment I introduced Z root D. This fields. Suppose you take P and L, fix an odd prime L. First do that. Some odd prime number L, take L bigger than 3. And consider again different prime numbers P and Q, odd prime numbers, and consider this number Q square minus P power L and write it as minus M square D. So you are writing M square to be the square part and D square free part. And then look at this ring, Z root D, it has class number CL minus D, what we denoted. Actually, we have proved that this number is very often it is divisible by L. But how often? So I ask a question that are there infinitely many pairs of PQ such that this number CL minus D here also I should say, CL minus D is not divisible by L. So that question I could not answer, but if answer to that question is yes, then I construct a polynomial of degree L minus 1 by 2 and I say that that polynomial takes infinitely many prime values. So Bunyakovsky conjecture is true for those family of polynomials. So only one polynomial for each degree L minus 1 by 2 where L is a prime bigger than 3, odd prime bigger than 3.